Hello everyone. So today we are going to look at the time required to empty a tank completely. Okay. So suppose we have a tank here. This is our tank. The total height of the tank is h. The diameter of the tank is d, capital D, and there is a hole at the bottom of the tank whose diameter is d naught. Okay. So these are the dimensions. So suppose initially the tank is completely filled. Okay. And the water starts to drain from here. Okay, so we have to find that how much time will be required to empty the tank. So let's find out. So for that we will do the mass balance first. Okay, so mass balance, we'll write the equation for mass balance. So we have the equation rate of mass in minus rate of mass out is equal to rate of change of mass, time rate of change of mass within the control volume. Okay, so this is our control volume. So suppose this uh, the whole tank system is our control volume. Okay, so now let at time t, at any instant, the height of the liquid in the tank or the water or if it is any liquid is at time t, it is small h. Okay, it is small h, the height of the liquid or water in the tank at any time, let it be small h. Okay, now this is our mass balance equation. Okay, rate of mass input, this dot here represents the rate. Okay, so rate of mass input minus of rate of mass outlet, or okay, is equal to rate of change of mass within the control volume. Okay, so suppose this whole system, this whole tank system is our control volume. Now as you can see, there is no input of mass, or we can say that no mass is entering into the tank. Okay, so the first term in this equation, let it be equation 1. So the first term in this equation becomes 0. This becomes 0 because no mass is entering into the tank. Okay, now the second term is rate of mass output. Okay, so this term cannot be 0 because some mass is going out of the tank from the bottom. Okay, so this is not equal to 0. Now we can write it as this term becomes 0, so we can write is that uh, within the control volume, rate of change of mass within the control volume is equal to minus of rate of mass outlet. Okay, m dot out. Now we have to write the mass within the control volume at any time t. Okay, so previously I have told you that at any time t, the height of the liquid in the tank is h. Okay, so we have to find the mass of the liquid, of this liquid. Okay, up to this height, up to small height, up to the height of small h. Okay, so this is the liquid, so we have to find the mass of this much liquid. Okay, so for mass we can write it as mass is equal to density into volume. Okay, and for volume we can write, for writing this much volume, we can write as area of cross section into height. And what is the height? This small h is the height. So this now see, the area of the tank, of this tank is constant. Okay, the area of this tank is constant, and the density of this liquid is also constant. So rho and AC are AC, area of the cross section, these two terms are constant. Okay, now suppose if we write it as if we write it here, rate of change for mass we write at density into area of cross section of the main tank into height. Okay, this is for mass. Now we have to write the rate of mass at outlet. Okay, or the rate at which the mass is going out. Okay, now for that we have to see the location from which the mass is going out of the tank. Okay, so we can see that the mass is leaving the tank from the hole at the bottom. Okay, so for that we can write, no, we know the mass flow rate can be written as density into volumetric flow rate. Okay, now if we write volumetric flow rate, we can write it as, so suppose this V is for volume. Okay, let me write it as volume. Okay, so we can write it as velocity, okay, into area. Volumetric flow rate can be written as velocity into area. Okay, so mass flow rate can be written as density into volumetric flow rate into area. Now the question is what area we have to take. Okay, so suppose this is our hole, so we have to take the cross sectional area of this hole. Okay, so I will write it as cross sectional area of hole. Okay, now we have to take the velocity at this hole. Okay, so let it write it at b hole. Okay, so we will write the rate of mass outlet as minus of density into velocity at hole into area of cross section of hole. Okay, now we can write it as okay, see, the density and the area of cross section both are constant because the area of the cross section of the tank is not changing. Okay, so both of these are constant, so we can write it as like this. Now density into velocity at hole into area of cross section of hole. Okay, this CS means cross section. Now we can simplify it as, let's cancel the densities because both are same densities. Now we can write it as dH by dt is equal to minus of ACS of hole by ACS, this is of tank, okay, and into this velocity at hole, this velocity at hole. Okay, now what we will write, okay, see, for the tank if we write the area of cross section, we can write it at pi by 4 d square. Okay, because the diameter of the tank is d, and similarly for hole, area of cross section of hole, we can write it as pi by 4 d naught square. Okay, and on division, and okay, so it will become dH by dt is equal to minus of d naught square by d square. Okay, and velocity at hole. Okay, now we have to find the velocity at hole. So let me call, so we will apply the Bernoulli equation. Okay, so suppose the system is such that we can apply the Bernoulli equation, that is steady, incompressible and irrotational flow. Okay, and the frictional effects are negligible, so we can apply the Bernoulli equation. So we will now the question arises about the points between which we will apply the Bernoulli equation. So for that, let me consider the point 1 here at the surface, or in this case, since the liquid uh, height is up to h only, so the uh, the point will be at this surface. Okay, and the second point will be at the bottom. Okay, so we will apply the Bernoulli equation between these 2 points. Okay, so point 1 and point 2. Now we can write the Bernoulli equation as P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Okay, so this is our Bernoulli equation. Now what we will do is we will cancel the terms. We can see that since the tank is open to the atmosphere, so the pressure at this point and at the point 2 will be similar, so we can cancel these two terms. Okay, because both are same. Now look at point 1 here. Since it is a free surface, the velocity will be 0 here, so we can uh, cut this term off. Okay, now what we are left with is we are left with V2. We will just shift Z2 with to this side, and we can change the sides we can write it as v2 square by 2g is equal to z1 minus z2. Now you can see the difference between these 2 points. The height between these 2 points is h. Okay, so we can write it as z1 minus z2 is equal to h. So what we have finally is v2 is equal to root 2 gh. Okay, so let it call as equation 3 and this as equation 2. Okay, so we will put equation 3 in equation 2. So what we have finally is, what we are left with is okay, let me adjust it. So we have dh by dt is equal to minus of d naught square by d square into velocity at hole, which is can be written as h to the power of 1 by 2. I written it like this because the next step will be easier. Okay, now take this h to this side and take this dt to this side. Okay, now we will integrate. So we have dh by h to the power of half is equal to minus of d naught square by d square into root 2g and this dt. Okay, so we can integrate it as, so suppose at time t is equal to 0, t is equal to 0, the tank is completely filled. So the height of the liquid in the tank will be capital H. Okay, since the tank is completely filled and the total height of the tank is h, so at time t is equal to 0, the h is capital H. And since okay, let's suppose we have to find the height at time t. So at time t, let the height is h. Okay, what we have assumed earlier, the same thing. Now we'll integrate it, so it will become 2 h to the power 2 root h. I think yes, this will become 2 root h, and the integration will be from capital H to small h. Okay, now minus of d naught square by d square into root 2g into t. Okay, so if we just simplify it further, we'll get t is equal to, okay, so the minus will go to that side, d square by d naught square into this root 2 uh, okay, so it will become like this root 2g, and it will be h to the power of 1 by 2 minus capital H to the power of 1 by 2. Okay, so but this equation can be confusing, so let me make it clear here. So this term is always less than this term, so this term is always negative. Okay, so if we just, okay, let me put this minus sign inside the bracket, so the whole term will become d naught square into root 2 by g into h to the power of 1 by 2 into h to the power of 1 by 2. Okay, so this is the time required to, so so finally we have the expression for the time required. Okay, now suppose we want to find the time required to completely empty a tank. Okay, so by completely empty we mean that at the final height of the tank of the liquid in the tank will be 0. Okay, by completely empty means at that time, okay, let me write it here. By completely empty means at that time at which the tank is completely empty, at that time the height is 0, means uh, at when the tank is completely empty, the tank is empty, at that time the height is equal to 0. Okay, so if we put h is equal to 0 in this term, in this equation, what we will get is t is equal to d square by d naught square into root 2 h by g. So this is the equation for the time required to completely empty a tank. Okay, so t is equal to d square by d naught square into under root of 2h by g, where capital H is the total height of the tank. Okay, so I think it is clear now. Okay, let me just briefly draw the graph here. Okay, so for this equation, if you want to draw the graph between the height and the time, so this is the height axis and this is the time axis, and if you want to plot the graph, it will be, suppose at time t, this is the height is h. Okay, and at t and at this time t final, the height is 0. Okay, so if you plot the graph, then it will be something like this. Okay, so this is the graph between the height and the time. Okay, so I think it's clear now. So that's all for today. Thank you.